fourth video in an introduction to a first course in modelling, analysis and control looks at automatic feedback. So what have we done in the first few videos? We've introduced the concepts of systems, behaviours, performance and the role of feedback to control behaviours. In particular, we looked at human-based feedback. So this video now demonstrates the popular PID compensator, which is a mechanism for automating feedback and used in many industrial scenarios. Controlling behaviour then. Having decided what behaviour means and what behaviour we would like, the previous video discussed how do humans ensure that systems behave the way we want them to. Now, humans tend to use a measurement, decision-action and wait for system to respond sort of feedback loop, and that was demonstrated in the previous video, and you can see the diagram down here, and we showed that it tends to be quite effective. However, what are the weaknesses with human policies? Well, you can see the main one: we get tired, we lose concentration, we make mistakes, and so forth. We don't like hostile environments, such as if it's too hot or too cold or too many chemicals. We are very expensive to pay. And in general, there are thousands of control variables and control loops in typical industrial processes, and we simply don't have enough humans to monitor and manage them all. Automation then. We need to automate the feedback process, that is, to get a computer to do the job for us. We've got electronic or other measurements available, and these can feed directly into a computer. The computer can then decide what control action is required. The computer then sends an instruction to the actuator, which could be a tap or something else, to move appropriately. And as you can see, this is relatively cheap, reliable, and the key thing is it operates 24/7, it doesn't get tired, it's much less worried about the hostile environment, and it's cheap. However, there is one issue. How does the computer decide what action is required? We as humans have had years and years of experience and we sort of know what to do, but we have to unpick that and tell the computer exactly how to make these decisions. The most common technique used in industry then is called PID, which stands for proportional, integral and derivative. Now, we will leave a detailed explanation for later. For now, we're just going to illustrate how effective this strategy is. The core point is the efficacy of the PID approach, ensuring the output reaches the desired value, and the key here is irrespective of uncertainty and disturbances which constantly occur in real life. First example then, we'll look at the cruise control, which we've looked at before. And so we're going to set the option to feedback, which is closed loop. And we're going to set the PI parameters both to be 0.08. Now, they aren't perfect, but they're good enough. Okay? So what we want you to do is watch how the computer automatically adjusts the throttle. So if you watch the throttle, you'll see it moves by itself because the PI is choosing the value it should have to ensure the speed is met. And this is irrespective of changes in slope, engine power and car mass. So here we go. If we find the cruise control, there it is. You can see I've set the parameters to be 0.08. It's in closed loop, so we can just start. The target speed is 30, and you can see the throttle is moving automatically. And the speed is changing, and you can see we're getting to the desired speed. Now, what if I change the slope? So I've changed the slope. This isn't enormously fast to react this GUI, but in a moment the slope will change there, and then you will see that the PI reacts. Can you see here how the throttle has reacted to this slope? And we've got very small deviation in speed. Now, what if we do something like change the mass? So the car is much heavier, and therefore it's going to be harder work getting it to go up this hill. And again, you'll see at some point there'll be a reaction when the mass actually changes, when the GUI picks it up. Doesn't seem to be reacting very fast today. There we go. Now you see the mass has changed, and can you see the throttle has gone higher and very small deviation in speed again. The next interactive slide then will look at the heat exchanger. So what we're going to do is set this to PI control and use the heuristic, which is some sort of automatic tuning rule. We're going to put the disturbances on and set the target temperature to be 30. And again, we want you to watch how the computer automatically adjusts the steam flow to ensure the desired outlet temperature is met. Now, this isn't going to be instantaneous because, of course, you can't do that. But it's fairly fast in terms of the dynamics of the system, about as fast as you could reasonably be. Okay, this one's still going. I'll try and shut it. Right, okay. So, here's our heat exchanger. So if I press continue and start, and what you'll remember here is we've got two disturbances. We can change the inlet temperature and we can change the fluid flow rate, and those are marked by these lines down here at the bottom, the green and the red line, which show you there's been a disturbance change. So the inlet temperature has changed or the flow rate has changed. But notice how the temperature is going to be controlled back to 30 degrees consistently. Okay, now it's not instantaneous. You see, it takes a while to react, and there's nothing you can do about that because of the dynamics of the system. It isn't going to happen straight away. But you can see automatically, you see this number here, the steam flow rate is being changed by the PI. You see, that's why that number is changing. It's automatically changing in response to these disturbances and trying to pull the system back. Now, if we want to show this a bit more slowly, if we put those off, so put those disturbances off, we can actually make manual changes to the disturbances. So we'll give it a time to settle. You see it's going to bring it back to 30 now, this PI compensator. So there, the temperature's come back to 30. All right, and now what I can do is I can artificially change the inlet temperature. So that's quite a big change, 6 degrees. But notice the PI is going to bring the temperature back about as fast as you reasonably could, given the size of this tank and the like. We could also change the fluid flow rate. And again, you see how the steam flow has been changed automatically by the PI, and it's bringing the temperature back. And that's really about as quick as a human could do it, if not maybe quicker. So, the conclusions. For many systems, it's important to control the output to a specified value and with specified behavior, irrespective of uncertainty in the model parameters and external disturbances. Automation of the measurement decision action feedback loop is commonly implemented using something called PID compensators. And we've shown here with two simple examples, this is very effective for systems with simple dynamics. And the truth is, it's pretty much as good as a human in practice, but of course a lot more reliable because it works 24/7. Now, this clearly was an introductory video. The rest of the module will introduce the mathematical and analysis tools that you need to look at feedback design in a more systematic fashion. And for example, how to actually go about choosing these PID parameters.